Hi, everyone. We'll get started here in about a minute or so. We'll let everybody settle in. All right. Hello, everyone, and thanks for joining us today to learn more about turbocharging your SCR with next generation technology, presented by CECO Peerless and hosted by Combined Cycle Journal. My name is Scott Schwieger, and I am the editor of Combined Cycle Journal, and I'll be today's moderator. I'm joined today by Vaughn Watson and Jeff Broderick from CECO Peerless, who will be collaborating on today's presentation and ensuing discussion. Before we get started, I'd like to go over some of the key features of this WebEx platform. You'll see you've got a dashboard with some controls on it, and if you're having any problem with the audio, you can just click on the audio icon, and from there you'll be able to troubleshoot your sound or given the option to call in. We also have a chat icon, which is where you'll be able to ask questions for the presenters that we'll go over during the Q&A session at the end, and we certainly ask that you send those questions in during the presentation so we can have them ready for Vaughn and Jeff after the presentation. And also today we'll be using polling, and the polling questions will be popping up on the right side of your screen, or this little button with the three icons, with the three periods in it will start blinking, and that's where you'll be able to access the poll and answer the questions today. So, the increase in intermittent renewable energy sources has brought about the need for gas turbines to operate in suboptimal modes where emissions compliance is a real challenge. At the same time, federal, state, and regional air quality regulations are becoming more stringent. Today, the presenters have a message for you. Just say NOx. We hope you leave here with a better understanding of common SCR performance issues, the mechanics of ammonia injection grids and how to avoid plugging, and the impacts of load changes and infrequent starts on SCR performance, and how next generation technology can address it. They'll also visit in-depth case studies on how AIG upgrades improved SCR performance. After the presentation, we'll have time for Q&A with Vaughn and Jeff, where they invite you to ask any questions that you have regarding emissions control systems. Our presenters today are Vaughn Watson, Director of Power Retrofits. He's been with CECO Peerless for over 12 years and is currently responsible for launching and integrating Peerless's new product lines that we'll hear about today. Jeff Broderick will lead us off today. He's the Director of Retrofit Sales and has been with CECO for over 6 years. Now I'll hand it over to Jeff to get the presentation started. And remember to chat in your questions in the side panel. Jeff?
Thanks, Scott. Good introduction. Good afternoon, good morning, good evening, everyone. Appreciate you all taking out your time to join us here. As Scott mentioned, we have some advancements in the world of SCR that we are eager to present to you today. And in the next couple slides, we'll go through that, and hopefully you're able to walk away with some enlightening information. So we always like to start with a slide that shows the overall system here. So, this is probably looks relatively familiar to a lot of you. Look a little bit like your units potentially that you're operating today. Although we're going to be going through some specific applications and features of an SCR system, it's always good to remember that even those specific parts are part of a larger system, and the goal of the larger system is to operate efficiently and safely. So although, we may be talking specifically about an AIG, there are other systems upstream and downstream of that AIG that can affect the overall performance. Go to the next slide. And to be more specific about the technologies we're going to be addressing today and how they can be applied for emissions control, we're going to be touching on what we refer to as the RACER. That's a next generation technology that we'll go into detail about and go over some of the benefits and features of it and how it may help your plant operate more efficiently. We're going to go into what some reagent options are to control your SCR, urea being one of those. May not be the most popular choice at the moment, or may not be the most typical reagent in a system, but we've seen an industry trend towards urea as it does offer a safe alternative to ammonia. Direct injection is another technology we're going to hit on. We'll go into the details of how that technology can be applied, what some of the benefits are of it, and what some feasibility aspects are that we need to take a look into before trying to apply it. And as well as the Edge AIG that we have applied on many units and seen some terrific results in terms of SCR efficiency. Just a graphical representation of two of those technologies that we're going to go into detail about here. Again, the RACER technology, which is on the ammonia vaporization side of the SCR, as well as the Edge AIG, that, as you can see, is the ammonia injection grid located upstream of the catalyst. We'll go into the details about both of those technologies, the benefits of them, and some analysis of how they can perform and improve your overall system. So with that, we'll get right into it. We'll get into the specifics, and we'll start off with the RACER technology, and Vaughn Watson, our subject matter expert on RACER technology, will take it from there.
Yeah, thanks, Jeff. Our RACER technology, or Rapid Advantage SCR, is one thing that we're going to be showcasing today. Many gas turbine plants today are operating to augment renewable power resources, such as wind or solar. These require plants to start up very quickly and achieve a peak power demand rate and vary the gas turbine load frequently to combat the variable nature of backing up a renewable resource. As we're reliant on the weather aspects of the wind blowing, the sun rising and setting with variability throughout the day, gas turbine flexibility and fast responsiveness to the changing demands is a utmost requirement. This can take its toll, unfortunately, on the exhaust system emissions controls and may require changes to the system to achieve the compliance during these operating conditions. If you could click for me. Many regulators are beginning to restrict the ability to operate outside of an emissions threshold during maintenance, startup, and shutdown, or MSS events. In addition, some permits are on a tons per year limit, therefore reducing the amount of NOx overall during the startup helps add additional run hours and starts to a plant's capabilities. It's about reducing the area under the curve. Could you click again for me? Thank you. The challenge becomes a bit twofold. It's a race between the exhaust temperature versus time curve and the catalyst reactivity versus temperature curve. The exhaust temperature is ramping up while the catalyst efficiency is increasing. At the same time, the ammonia must have adequate temperature to be vaporized. We wish to begin ammonia injection sooner in the process so that we can begin reducing NOx in a short amount of time after startup as possible. The ammonia injection rates during the startup period are nearly double or higher than steady state operation. So not only do we need the heat input immediately to vaporize, we sometimes need twice as much heat during the startup period to vaporize the larger quantity of ammonia during the startup cycle. The key there is to be able to vaporize the large quantity of ammonia rapidly and accurately deliver it to the catalyst as the catalyst is moving up in its efficiency curve without exceeding ammonia slip limits. Using our RACER technologies, we can very, very quickly vaporize the ammonia and begin ammonia injection as little as minutes after startup. you could click for me. On systems that rely on electric heaters, the additional electric kilowatts required to quickly vaporize the quantity of ammonia needed at startup becomes extremely large and begins to be cost prohibitive very rapidly. On the other hand, systems that rely on hot gas recirculation fans, the challenge is the gas drawn off of the HRSG is not at enough temperature during a startup to adequately vaporize the ammonia. We have successfully hybrided electric and hot exhaust systems together. However, the racer system that we've developed recently has become the number one choice for these fast start systems. Peerless has these proprietary equipment designed to achieve emissions compliance during these startup and transient conditions. This equipment is a suite of solutions aimed at fast start and transient load operations on combined cycle gas turbine plants. And again, it allows us to rapidly vaporize ammonia while controlling NOx and slip during shifts in load. In addition to the startup and transient operational advantages, a major advantage to this technology is it is extremely economical to operate. When compared to the large parasitic load of electric vaporization or some of the higher maintenance costs of a hot gas recirculation system, the racer technologies offer a substantial operating expense savings, in many cases offering a return of investment of as little as a year or more. We also have an online calculator where you can calculate your plant savings by going to justsayseco.com. And we can talk to you on a plant-by-plant basis on how to improve your operational savings by using our racer technology and increasing your operational efficiency during these fast starts. And with that, I'm going to hand it back over to Jeff to talk about our next topic.
Thanks, Vaughn. Yeah, Scott, if we could go into the next slide, that was a good overview on Racer Technologies. If anyone has any questions on that, feel free to put it in the chat and we can address those at the end of the presentation. So it was a good segue discussing some options on how you can vaporize ammonia and introduce it into your SCR system. What we want to focus on now is some of the different options we have as a reagent. We will get into the specifics of urea, but let's first cover some of the more traditional options we have. So in an SCR system, really the function of the storage and handling system is to store the reagent that we're going to use to generate ammonia gas in front of the catalyst. So there's some very straightforward ways to doing that, and some that require a little bit more equipment, engineering design. A lot of the decision-making factors in which reagent to use are based on the cost benefit versus the risk. And that risk typically comes in the form of safety and the safety requirements required to store ammonia at your site. A very common reagent to use on an SCR system is anhydrous ammonia, especially larger units. The advantage here of anhydrous ammonia is it is not stored, you don't have the liquid mixed into it. It's straightforward. You pull off the tank as a gas, you introduce that into a dilution air system, and you deliver that to the AIG in front of the SCR catalyst. It's a very straightforward way of effectively reducing NOx. Usually that is stored as nearly 100% ammonia gas in a pressurized steel vessel. So the tanks are often large steel pressure vessels kept under pressure, and you pull off the gas from that tank and introduce it to your system. obviously ammonia has safety concerns with it, especially when it's pure ammonia gas. If there were to be a leak in that tank or in the piping or in the delivery system, it could be a major health hazard to the personnel of the plant. It only takes a few hundred ppm of that raw ammonia to be fatal to the people exposed to it. So clearly, there's a lot of HAZOP procedures, permitting processes, and safety measures that need to be taken in consideration when storing ammonia gas. Typically, you're going to need ammonia monitors throughout the plant, at the storage area, at the delivery skid, up near the AIG, and all that. So a lot of risk factors there that need to be taken into consideration if you have that, or if you're thinking about adding that capability to a facility. The advantage of it is, like we said, it's very straightforward process. So the cost of it is low. You don't need to vaporize that ammonia like as you would if it were a liquid. You may need to heat it to keep it in the vapor phase, but you're not necessarily vaporizing it. So clearly a straightforward process, but one that comes with risks for sure. There may be some permitting challenges with the delivery process of it when you need to get your tank refilled. So those are all things that need to be considered with that type of system. Moving down the line, aqueous ammonia, possibly the most typical choice in new SCR systems these days. Again, it's ammonia, but it's mixed with water. Obviously, the fact that it's diluted with water makes it a safer alternative. If there were to be a leak in that tank or in the piping or the delivery system, it is still hazardous, but obviously less hazardous than just having the personnel exposed to the gas. Typically, that's in the form of 19 or 29% ammonia by weight in a demineralized water solution. Again, it's stored in what is typically a steel tank under pressure, so the vapor doesn't come off of it. And you pull that liquid off the tank through your fluid handling system, and you introduce it into a vaporizer. Maybe the biggest cost adder here between an anhydrous system and the aqueous system is the fact that you now need to vaporize that liquid into ammonia gas before sending it through your AIG. So clearly there's going to be some cost adders to have the larger blowers and heaters or hot gas fans, whatever it might be, to vaporize that ammonia into a gas. Again, you're probably going to want some ammonia area monitors in the storage area and the fluid handling area, just in case there is a leak or a spill. Obviously, safety is the #1 concern. Safety being such a concern is why urea has become maybe more and more of a popular choice. We see that graphic there of what's called blue DEF. So not everyone may be familiar with urea. Urea became a popular choice in SCR systems starting in the mobile industry. Cars, trucks, buses, things of that nature, that would not be a good idea to have an ammonia tank on the vehicle in case there was an accident. Went with urea-based systems. So you can actually buy 32% urea, at a truck stop to fill up your diesel truck, by the gallon, and it's called DEF, diesel emissions fluid. It isn't only used on diesels. It is used widely on many SCR systems, but just show that to show how common it is in certain areas. Typically, when urea is on site, it's stored as a liquid. There is a process where you can store it as a solid or a powder and make your own solution on the site. But in our experience, the most common method is to store it as a liquid on site. One of the major differences is it doesn't need to be kept in a pressure vessel, doesn't need to be kept in a pressurized tank. It can be stored in an atmospheric tank. It comes in different solutions. 32%, as I said, is the diesel emissions fluid, DEF, concentration, but it also comes in 40% and 50% regularly available in many regions for different concentrations. That allows you to sometimes store less water, obviously, and more solution. Clearly, because it's non-hazardous liquid, there's less transportation and permitting risks and very little safety concerns for the plant personnel. Getting into a little bit more detailed into the urea, now that we've talked about the differences between them. There are some challenges with urea. You don't. It's not the same as an aqueous ammonia system. There are different challenges and considerations that need to be taken into consideration during the design of a system using urea. Urea is very corrosive as a liquid. For that reason, it's not going to be stored in a carbon steel tank. It'll eat right through it. So the storage tanks are typically either stainless steel, which can be expensive, or there are less costly options for what are usually FRP or fiberglass reinforced plastic. Those tanks come in a variety of sizes. They even come in double wall tanks, and we'll get into that a little bit. All the piping, all the anything in the wetted parts need to be stainless steel, and you need to take a close look at the seals. Viton is a good seal for this type of solution. Another challenge with urea is the temperature limitations. You will find that it has different, depending on the concentration, has different freezing temperatures, but you do want to avoid having the urea salt out in your system or crystallize in your system. It could cause some major headaches in the fluid delivery system. So a lot of plants we'll see need to heat trace and insulate their lines in order to use a urea-based system. Obviously, you're going to take into consideration how much capacity. And again, there's a wide variety of tanks available, whether that's stainless steel or FRP. One of the advantages of the FRP is they can easily be fabricated as double-walled tanks. The combination of the urea solution not being hazardous and using a double-wall tank can, in some cases, eliminate the need for a containment area around the tank. Obviously, that is site-specific, but in some cases, that is an option. So something we've seen in the industry is reagent conversions of existing systems. So there are systems out there that, existing anhydrous ammonia systems that, due to some safety concerns or more availability of aqueous ammonia, or switching to aqueous ammonia, or potentially even aqueous urea, or aqueous ammonia systems converting over to aqueous urea systems. May not be as expensive as you might think. There are some parts between them, depending on what system you're going from to where you're going to, that may be able to be reused. For instance, an anhydrous ammonia tank may be able to be repurposed as an aqueous ammonia tank. Obviously, with an anhydrous ammonia, you're not going to have the vaporizer, so the addition of a vaporizer would be needed. The addition of the fluid handling system would be needed. So if that's a consideration in any of your facilities, those are obviously things to take into account. Space availability and power consumption of these new pieces of equipment. If you're going over to urea system from an aqueous ammonia system, maybe unlikely that the tank is going to be compatible unless you have a stainless steel tank there already. So a new tank may be needed. It's possible the fluid handling system could be needed. The difference between the amount of ammonia injected and amount of urea injected, it typically isn't so great that it's out of the range of the fluid handling system, but obviously need to take a close look at that. And one of the bigger challenges with the urea versus the aqueous ammonia is you do need more energy to vaporize and decompose the urea into ammonia than you would just simply vaporizing the water out of the aqueous ammonia solution. So if there is an existing vaporizer on site, chances are it will need to be upsized, whether that's larger blowers, larger heaters, both, whatever it might be. So that's definitely something that needs to be taken into consideration when thinking about this conversion to the safe alternative of urea. It may require an upsize in a vaporization system, or maybe an additional vaporization system to get the energy needed to not only vaporize the water out of the solution, but decompose it to ammonia prior to reaching the AIG. So our first poll question of the day. What type of reagent are you using at your facility today? If you have an SCR system that you're operating, if you could tell us what type of reagent you're using, anhydrous ammonia, aqueous ammonia. aqueous urea. Lots of votes for aqueous ammonia. To be expected, I think. All right, thank you for the feedback on the poll. Appreciate that. So another technology we want to get into that, for combined cycle units may not be, well, certainly wouldn't be the typical solution. Typically what you're seeing is like we've been talking about, is let's say an aqueous ammonia system with a vaporizer, whether that's hot gas fans or electric heaters, producing the hot gas needed to vaporize that ammonia and sending it through some interconnecting piping to ammonia injection grid, introducing that ammonia gas in front of the catalyst. A very efficient, typical way of reducing NOx in a combined cycle plant. We can advance one slide. There are other options for that, though. Something we refer to as direct injection. So direct injection SCR is a method of supplying ammonia vapor, ammonia gas, to the SCR system gas path without the need for a vaporizer or the AIG. So what it's doing is it's using the heat energy from the main exhaust gas to vaporize the liquid, and whether that's ammonia or urea, and turn it into an ammonia gas upstream of the catalyst. Now, on these types of units, there are many feasibility considerations that need to be taken into place before deciding whether this is a good option for your unit. One thing is there a duct burner in the gas path? If you're injecting an ammonia solution and it passes over the heat of a duct burner, much of that ammonia is going to go to NOx. It's going to burn up the ammonia, it's going to go to NOx, and you actually end up increasing your NOx potentially. So if there is a duct burner in the gas path and the only way to inject is upstream of that and the catalyst is downstream of that, there would certainly be some challenges with implementing a direct injection system. Again, the typical SCR system with the vaporizer leading to an AIG, the major advantage of the AIG is you can get very good distribution of ammonia across the catalyst phase. That's the greatest challenge in direct injection. Oftentimes able to be overcome, not every time. So what is the cross section of the duct in which you may be injecting that liquid ammonia or liquid urea into? Is it feasible to get enough coverage of that ammonia to then mix out with the exhaust gas prior to the catalyst? How much residence time is there between the point of injection and the face of the catalyst? If it's a small duct at very high velocity, the reaction time may not have enough time for the reaction to happen or to evenly distribute. What is the required ammonia to NOx mixing? So on very high reduction units or on ultra low outlet NOx units, if you have a 2 ppm unit, sometimes the catalyst folks are telling you need a very tight RMS or ammonia to NOx mixing number that may not be achievable no matter how many injectors you put in there. It may be that you need an AIG. Are there CO or VOC reduction requirements in your unit? If the situation is that you have a separate catalyst, CO catalyst or VOC catalyst upstream of your SCR catalyst, you're not going to be able to inject upstream of that. As ammonia passes through that catalyst, again, you're going to end up oxidizing and making NOx there. Certainly some advancements in catalyst technologies that allow direct injection to be more frequently implemented, multi-pollutant catalyst or dual function catalyst, whatever you might call it, that can reduce NOx, CO, and VOC all in one layer of catalyst, has made it more feasible in many conditions to implement direct injection. So situations without a duct burner and with a reasonable size duct and enough residence time, direct injection could be a very good solution, even if you need those CO and VOC reductions with a multi-pollutant catalyst. So if we're injecting the liquid directly into the gas path, we're bypassing the need for some separate equipment, right? We don't need that separate skid that has the dilution air blowers and heaters or the hot gas fans. We have less equipment there. So there's obviously a cost savings with the types of systems that can be direct injection method. The AIG doesn't need to be there. So a lot of the valving, the IC piping, and the grid itself does not need to be there. So there's clearly some reduced capital costs there. Without the need to operate those blowers and heaters, without them even needing to be on site, obviously there's some operational savings there. You don't have the hundreds of kilowatts needed to vaporize the liquid into a gas. You're using that heat energy just from the exhaust gas, the main exhaust gas, as your medium to vaporize the solution. And again, ease of operation, less, fewer moving parts, easier it is for the plant personnel to operate. There are other challenges that could be a little less familiar. So graphically, here's how a system could look. You can see there's some injectors mounted on the duct on the sidewall. So that's different than your typical AIG system. So plant personnel would need to become familiar with that. But the injectors get mounted on the wall. They spray a liquid. Typically, it's a liquid and air mixture, so you get the atomization needed to carry the spray into the exhaust gas path and allow it to mix in with the exhaust. So those injectors obviously need to be design engineered for whatever the application is in terms of flow rates, temperatures, pressures, and all that. Definitely need to take in consideration where those injectors are located, how they interface with your piping. Obviously, as we mentioned, let's say if this was a urea direct injection system, you don't want that liquid urea coming in contact with that carbon steel duct. So you're going to want to make sure the system is designed as such to not cause any other damage. On the other picture, you see what we reference to as a metering skid, which allows some controllability to the unit. So that would look, that's similar to the manifold for the AIG. This is the control skid for those individual injectors. Case study here on when we implemented direct injection not too long ago, a couple of years ago, up in Northern California. This was a bit of a unique situation. They had an existing emissions control system on it. You can see it's called a SCONOP system there. It was actually very efficient at reducing NOx and CO emissions. From an emission standpoint, it was efficient, but it was not efficient to operate or maintain. There was a lot of headaches that this particular facility had with their system in terms of maintaining it, doing a lot of replacement parts, a lot of damper changeouts, a lot of catalyst cleanings, things of that nature. So they were very motivated to retrofit a more user-friendly system onto their units. So the solution that we implemented was actually a urea-based system, direct injection system. So we were able to, you can see the CFD graphic there on the left, install some injectors on the sidewall, have them spray into the sidewall. About 10 gallons an hour of urea was sprayed into the sidewalls and mixed out in the exhaust gas path, mixed very nicely. In this situation, no duct burner, used multi-pollutant catalyst. So we were able to reduce NOx, CO, VOCs all in the same layer of catalyst using urea-based direct injection. In this particular case, the pressure drops were dropped greatly across the unit. The ancillary equipment associated with the old system was removed, and we were able to increase their power output by quite a bit, giving them a pretty good ROI on this system. A little bit more data on the next slide. Just showing some of the numbers there, 50 to 100% load range data. You can see some of the very low NOx numbers under 2 ppm, 94% reduction in one case there. And again, the very low CO numbers, and even the ammonia slip numbers were quite low. So, a very, very highly efficient emissions control system here um, as a retrofit direct injection application. So that's just an example of how it can be done, and a little bit of data, a little bit of graphic there on how that's carved out in a retrofit application. So another poll question here: does your facility running your SCR system, is there a duct burner upstream of your SCR system? How many of you have a SCR system that has a duct burner upstream?
Looks like the large majority have a duct burner upstream of their SCR.
Yep. All right. Not too surprising there. So those could be a challenge for this type of technology. With that, Vaughn's going to go into the details of the Edge AIG system as our final piece of advanced technology.
Yeah, thanks, Jeff. As Jeff kind of alluded to earlier, one of the things that's most critical to these high-performance SCR systems is the ammonia to NOx distribution. And one of the biggest improvements to an existing SCR system would be improving that, that ammonia to NOx distribution by improving the ammonia injection grid design. So the ammonia to NOx distribution plays such a critical role in the overall SCR performance. When we talk about meeting permit level emissions, if your AIG is, say, plugged or has degraded, or you are facing design challenges in achieving current day emissions concerns, one of the things that we would look at is the ammonia to NOx distribution. When we are looking at a new SCR catalyst, a couple of the key factors there is what's the velocity distribution, what is the temperature distribution, but the most important one that we've seen is the ammonia to NOx distribution. And by improving that or getting it closer to sub 10% RMS, we've seen a major increase in the overall SCR performance. By improving this ratio, we're improving the NOx performance, reducing the ammonia slip that plants are seeing. We are decreasing the ammonia consumption that plants are using, and in many cases, extending the catalyst effective life by utilizing some of the margin that they have left in their existing catalyst. If you could go to the next slide for me. So Peerless's patented Edge AIG design, which has been Peerless's standard since about 2007, has kind of changed what common ammonia to NOx ratios we see out there in the SCR market. A lot of times back in the early 2000s, 15% RMS ammonia to NOx was very common. However, with latest gas turbine technology and latest air permit requirements, that's simply not good enough to achieve, say 2 parts per million NOx, 2 to 5 parts per million slip, greater than 95% DNOx efficiency. So by improving that ammonia to NOx distribution number, we've seen a number of plants be able to achieve modern day technology on catalyst that's 10 to 12 years old without having to replace that. One of the things that's also a great side effect, so to speak, is that the cross-sectional area of our new AIG Lances is inherently less susceptible to plugging. So that in turn means less maintenance costs and less outage work that needs to be done to clear plugged AIG holes. So this gives us a distinct advantage. Again, it's been our standard issue technology for over about 10 years now, and we've been retrofitting a lot of plants with this design to allow them to achieve current operating conditions. How this works is on conventional AIG designs that were probably prevalent in the late 90s, early 2000s, which was a circular lance with either holes at 12 and 6 o'clock. Those designs relied on low velocity wisps of ammonia that required quite a bit of residence time and mixing distance to achieve the distribution that it was able to prior to the face of the catalyst. In today's Peerless Edge AIG design, we're allowing turbulent mixing to take place over the cross section of our lance by the wake that is forming on the backside of our lance, as well as instead of low velocity wisps of ammonia being injected, we are now dealing with jet penetration. So we are increasing the pressure within the lance. We are effectively getting further into the exhaust stream with that mixing and putting our ammonia plumes right in the line of our wake that's created with our AIG design. And that has seen major improvements in ammonia to NOx efficiency, as well as the distribution across the entire cross section of the duct. A couple photographic pictures of our Edge AIG design. We do use this diamond-shaped cross-section, hence the name Edge, and that allows for turbulent mixing without the need of additional steel baffles or baffle plates attached to the AIG. It also allows us to inject directly in the line of the catalyst without having to eject at 12 and 6 o'clock and rely on the gas flow to take us there. So this design not only has been proven, but it's also become a really big game changer for us on a retrofit basis to allow older plants to meet newer technological requirements. One of the ways we can, I guess, verify our claims is by going in and tuning ammonia injection grids, but also going in and sampling the exhaust gas to measure the ammonia to NOx upstream and downstream of the catalyst in order to show that by improving the ammonia to NOx RMS values that we're able to improve the SCR performance as a whole. In addition, we're able to take our better technology and tune it to meet the utmost performance it's capable of seeing right after installation and during a quick outage. A big issue we experience with our experience in the field is AIG plugging. Usually it's ammonia byproducts that are carried over or actual degradation of the metal, like rust, being impinged on the orifices of the AIG. Mill scale and rust can break free over time. You know, some of these plants are 20 years old, and rust deposits are steadily making their way into the holes of the ammonia injection grid. With the Edge AIG design, the rust and any other debris that's in there has a spot to accumulate without plugging up the holes. And one of the big issues with plugging is that as soon as it plugs, you can't predict the ammonia to NOx shift in distribution. So, you know, the ammonia to NOx ratio shifts as the AIG gets plugged or fouled. And by having a design that not only improves the ammonia to NOx ratio, but also having something that kind of combats that inherently, makes for a really great product. A quick case study. This is a plant in the southeast United States. They had 9 HRSGs. We had worked with them because they had noticed some AIG fractures and some other issues going forward. Peerless had gone in and done 1 unit of Edge AIG upgrade. At the conclusion of that, they went ahead and did the other 8. We had seen their ammonia consumption go from about 600 to 700 pounds an hour down to about 300 or 400 pounds an hour, depending on load. And the plant was extremely pleased. After doing some tuning and some catalyst sampling, they were able to estimate an extension in catalyst usable life of about 2 years. So not only did this reduce their chemical usage, improve their NOx control, and improve their ammonia slip, but they also were able to stave off a capital catalyst expenditure for up to 2 years before putting that back in their maintenance budget. So this was a huge win for Peerless and for the end user. And that was 9 units of Edge retrofit that we've done. I did mention earlier that this has been our standard design since about 2007. In Peerless's history since 1988 of doing SCR systems, We've done 1,032 SCR systems worldwide, of which about 42% are of the Edge AIG design, again, since about 2007, and as well as the retrofit units we've done as well. So this is a proven technology. It's an easy retrofit that can be done in a short outage, as well as a lot of things we do don't disturb adjacent equipment, such as external manifold piping and so forth. So to recap real quick before the Q&A section, the next generation emissions technologies can increase plant efficiency and performance. We've seen the reduction of parasitic load for ammonia vaporization by 80% or more using the RACER technology, reducing the ammonia consumption by up to 40% using our Edge AIG design. A combination of these technologies, whether it be direct injection or RACER, has seen DNOx of greater than 96%, CO destruction by greater than 98%, and VOC destruction between 40 and 50%. And this is what the industry is trending towards as far as the emissions going forward from 2020 and beyond. Quick note about the remaining CECO environmental product lines. In addition to Peerless's SCR experience, we have a number of sister companies that specialize in dampers, expansion joints, silencing technology, low NOx burners, SNCR technologies, and gas separation and filtration. So between the CECO environmental family of brands, we can help any plant achieve their equipment and environmental protection needs. And with that, I'd like to start the question and answer.
Thanks, Vaughn and Jeff. Before we get into the Q&A, some questions came through based on ammonia vaporization. So I'd like to open up one more poll for the attendees, and it's, what heat source does your facility currently utilize for ammonia vaporization? And that's going to pop up right now. While this poll is running, a question came in. What vaporization technology has the lowest life cycle cost of ownership?
As far as reagent type, obviously anhydrous has the lowest. As far as life cycle cost of the vaporization technology, I would say RACER because it's a newer technology, but as a fallback to that, I would say electric does.
Okay, poll results are in, and the majority use electric heaters.
Well, that's good. It's a great way to get online quickly. Unfortunately, you're using hundreds of megawatts, as Jeff mentioned earlier, to vaporize that ammonia. So that's hundreds of kilowatts that could then be sold or put to other things in the plant.
All right, I think it's time to move into the Q&A.
I got a couple questions here. Currently, how many units do you have installed with the RACER system? We have 14 units installed. How many of those service HRSGs? Well, we have some regenerative systems that are on about 8 frame 5 units in Mississippi and Kentucky, I believe. Do you expect a faster catalyst degradation by speeding the reagent injection before the minimum operating temperature? That's a really good question. So the question is, do you expect a faster catalyst degradation by beginning ammonia injection sooner? The answer is no. We are kind of pre-saturating the ammonia into the catalyst as part of the RACER controls and allowing the time versus temperature curve to begin that reaction at a sooner rate. Our big issue, or one of the main challenges, I should say, is having the heat source required to provide that vapor ammonia over to that catalyst in a quick amount of time.
Okay, how difficult is it to retrofit a current AIG to add the racer system?
We are doing several in this upcoming fall outage, most of which are an 8-day outage. In many cases, we are simply scaffolding downstream of the AIG. We are cutting off the existing round AIGs in many cases at the wall, and then fitting our edge lances to the stubs that stick through the wall. There are a few distinct cases where that's not feasible, but the most oftentimes we see 8 to 10 day outages, and we can do 2 units simultaneously with the manpower we have available.
Okay, we've got some questions in here for Jeff regarding direct injection. How do you tune direct injection systems?
Yeah, so one of those photos that was shown of the metering skid, there is the ability to bias or balance the ammonia or urea going to the injector. So there's the opportunity to change the pressures and flow rates of both the air and the liquid to the injectors. And there's also an opportunity to increase or decrease the penetration into the duct wall of the injectors. So that's something that's preliminary done with CFD modeling and then done in the field as a tuning process during the startup of the unit. So there is some tunability to the direct injection units.
Can direct injection be used as a backup system for the AIG, like if your principal skid fails?
I'd say yes. That's a good question. That's a unique approach to adding some redundancy. So if your vaporizer was to go down, you could redirect the fluid to the direct injection injectors upstream in that inlet duct and get NOx reduction that way. You know, this is all assuming that the feasibility aspects of the direct injection system have gone through, such as not going through the duct burn. But yes, that is feasible.
And that is something we've actually done on some units, not in the HRSG world, but in other types of combustion sources.
Right.
Can you explain the mixing profile? And are you using static mixers?
Customized per approach. So yes, in many cases we've used static mixers. That may be something like a perf plate upstream of a catalyst. Maybe something a little bit more detailed, either upstream or slightly downstream of the catalyst or of the injection location. So we do take a close look at all of that in the design period.
Have you noticed any corrosion problems on fin tubes and the Herzig in general when using direct injection?
No, because we've taken great care to avoid that. So we make sure we're upstream far enough where we're not injecting any liquid onto those tubes. So the vaporization of either the urea or ammonia is complete by the time it's reaching any of those tubes. So we have not experienced that.
How does turbulent mixing affect overall turbulence and gas flow within the Herzig? Does it cause strange harmonics or possibly flow issues?
In terms of the edge AIG, it is negligible because the turbulence at the injection point is localized to the lance, and the overall DP across the edge AIG lances is minor. It's a 0.1% at best, and that's more of a localized effect than it is a macro effect across the millions of pounds of exhaust flow going across our AIG. Now, in terms of direct injection, I'll let Jeff answer that one.
Yeah, it's something that needs to be considered in the mounting design, injector design, and penetration depth. So it is something we include in our analysis and design towards to prevent.
Okay, back to the edge. Is the edge AIG adjustable for tuning of the distribution system?
Yes. So the existing manifolds, or in a lot of cases, we're upgrading folks' distribution manifolds to allow for tuning and adjustment. It is adjustable. The other thing we look at is the hydraulic distribution along the length of the lance. We want the same amount of mass of ammonia coming out the first hole as the last hole of the AIG. So our maldistribution across the lance with temperature effects and flow effects to be 0.1% or less in order to achieve good hydraulic distribution in the duct. As far as tuning that on these retrofit bases, I didn't include it in this presentation, but we do have some animations I usually show. We're able to adjust the degrees of injection at the top and bottom and other locations within the duct of tilting the edge AIG lances inward or outward as needed to assume mezzanine effects or other baffling upstream of us to keep the ammonia out of a dead zone.
Okay, have you witnessed any erosion at the edge AIG lance due to their unique diamond shape?
No, in fact, if anything, we've seen a more resilient design. The square tube cross section is a lot more rigid than the pipe across the length. The one thing I didn't mention earlier is conventional AIGs were hand drilled orifices in those lances due to the manufacturing techniques. Our new lances are laser drilled and deburred, so there is no surface that would be eroded by just gas vapor going across. And again, by keeping the rust particles and other things that could be contained in that stream from impinging upon the whole design, it keeps that erosion to an absolute minimum.
Okay. Does Peerless have any experience with using cool air fans for dilution and heating the air inside the Herzig with a separate heat exchanger?
We do. I've done a few of these, including one in Great Britain not too long ago. And those are done in a number of different ways. One, by shifting where the heat transfer of an HRSG itself takes place in order to increase the startup of the limiting factor there is the metal temperature of the drums on its ramp rate. But yes, we can do that. We have experience doing that, and we have the CFD capability of designing those systems.
Great. Question for Jeff. Have you considered direct injection without catalyst?
So that would essentially be SNCR, which we've done many of. You don't get the reaction you need for NOx reduction at the temperatures we're seeing on these types of units. The temperatures you're going to need for NOx reduction with SNCR, non-catalytic reduction, are up in the 1800 degrees Fahrenheit range, give or take.
Can you perform an engineering analysis of our existing facilities, which include CFD studies?
Happy to do so.
Yes, we do that quite a bit.
One attendee came in late and had a question that he may have missed out on. Can you address how you heat if you are eliminating HGP fans or electric heaters on the AVS?
This is in response to our racer technology, I'm assuming.
Yes.
The racer technology, one design, our most prevalent design, uses gas burner technology. So we are taking a tap off of, say, a duct burner or other fuel source, heating the air, the ambient air, with a gas burner, and being able to vaporize the ammonia with that stream. The beauty of that is anything we create with our gas burner gets treated by the same SCR that your gas turbine is treating.
And that burner could be of multiple fuels, whether that's gas, propane, oil.
Okay. Are there turn down limitations for the direct injection system?
Yeah, certainly a limitation, but not really any different than on a typical system. So the injectors are able to operate across a wide flow rate range, and if needed, injectors could be taken out of service for ultra low flows.
Okay, and we've got a question here related to your sister companies. Do you have any SECO sister companies who offer metal expansion joints?
We have done metal expansion joints. Our primary expansion joint is a fabric bellows style with internal liners, like you would see on your GT to HRSG expansion joint or your stack bellows to your HRSG.
Okay, gentlemen, I think we've exhausted all the questions today. And right on time.
Great. A lot of good questions.
Yeah, well, thanks so much for your presentation, gentlemen. If you'd like to contact Jeff or Vaughn, here's their contact details. We'll be sending you out a link to the recording of today's webinar if you'd like to revisit it or share it with someone else in your organization. And you can visit Just Say Seco to download some collateral from Seco and also check out some of their really interesting podcasts that they've been producing over the course of this unfortunate pandemic period. Well, thanks for joining us today. And we certainly appreciate your support of CCJ and of Seco.
Yes, thank you. Thank you, everybody.
Thank you for your attendance.